I'll have our matrices packet here. So when you say the word matrices, you're talking plural. A matrix, okay, is the singular term, and a matrix is a rectangular array of numbers. A rectangular array of numbers. And again, what I just said was plural is matrices. Matrices are often named with a capital letter. So I might say that is matrix A, or that's matrix F, okay? Kind of like we used the alpha symbol to to name angles. You just have a certain way to name them. So here's an example of a matrix. The entries or the element are the individual values. Okay, so 6 is an entry or an element. -2 is an entry or an element, so on and so forth. The dimensions of a matrix is always the number of rows times, and then you have an X there, so it's blank by blank. And you say it's rows by columns. The order of the dimensions does matter. It's always row by column. And that helps, and that is important when we go to talk about how we can use mathematics with matrices.
Are O's like lowercase while the other ones are uppercase?
Yeah. I do have actually a little side clip here for us to watch. Now, I just remembered some of us might be wondering, why are we talking about matrices? Why? How does something like this even apply to mathematics? So I'll open up this video here.
Will the matrices be on our final too?
No, I'm not going to put them on the final.
I feel like every time we do a math test, we end up learning this stuff right after.
This unforgettable vacation memory.
See if I can skip this video real quick. Oh, Peyton, I'm not presenting my screen, am I?
No, you're not.
Oh, goodness. This is an awesome video I'm recording. I'm yelling at you and myself. All right, I'm presenting. Peyton can see this now. He was probably able to follow along. Let's see if I can.
It didn't actually begin here.
Advertisement.
This memory began when Dad booked his family summer vacation.
There we go.
We got to keep going. After another hour, we write the same percentages.
And
This video is sponsored by Dashlane.
Here we
Circuits
go.
and electronics, image processing, computer graphics, quantum mechanics, the Google PageRank algorithm, any kind of network, other stuff. These are the kinds of things where matrices are used and extremely important for understanding or analyzing different systems. And although I can't discuss everything in one video,
Okay, in the back of the room, were you able to hear everything you said at the beginning at all? Okay. We're really only watching about 20 to 30 seconds of this video, but he names a lot of things that were in mathematics or in real life where you can apply matrices.
this video is sponsored by Dashlane. Circuits and electronics, image processing, computer graphics, quantum mechanics, the Google PageRank algorithm, any kind of network, other stuff. These are the kinds of things where matrices are used and extremely important for understanding or analyzing different systems. And although I can't discuss everything in one video, this should give you some insight into the applications of matrices beyond what an introductory course might include.
Okay, so this video really, I've watched it up till, I don't know, about 15 minutes of it just because I wanted to see where he went with things. It gets very complex very quickly, okay? And as you go through Math 2 and Math 3, in Math 3, you're going to pull back into and maybe at the end of Math 2, but I think it's mainly in Math 3. We're going to pull back into matrices and use it for solving and looking at different things. So how many of you have used Excel before, the program Excel, Microsoft Excel? Okay. Have you looked at any of like the formula? Have you done any formulas or anything? Yeah, so an Excel is a spreadsheet, right? You maybe have used Google Sheets, and so you can like put almost it's like computer programming into Excel or Google Sheets and have it output certain results for you. And so matrices are a way that we can kind of organize and say, I want this to happen here, I want this to happen there. And so I know that this year Mr. Hebert was using matrices. They are introducing and starting kind of with Excel and showing like how you can have things output and whatnot. So it's kind of just a basis. There's a lot of mathematics that branch off of matrices, and we just wanted to, because we had some extra time before the final, give you that exposure this year. Okay. So if we go back here to our notes, a square matrix is a matrix with the same number of rows and columns or equal number of rows and columns. Square same or equal is the appropriate word right here in this blank. So example number 1, what are the dimensions of this matrix? And come back up here, remember it says it's row by column. So how many rows does this have? 2 rows. So rows go left and right, columns go up and down. So you write that as 2x3, 2 by 3.
Does it need the line under it?
Nope, you don't have to have the line under. It's just kind of like an answer blank here. What about the second example? 1, 2, 3, 4 by 5. 4 by 5. And then we have the word equal matrices. If I wanted to say this matrix is equal to this matrix, every single entry would need to be the same or equal. Okay, so here's an example of equal matrices. If I set this matrix equal to this one, 3, 6, 9, 5, they all correspond. Okay, this is a non-example. 1 is in the same spot as 1, but as soon as I go to 4, this is the first row, second column is a 4, first row, second column is a 2. So I can't, they don't correspond. This is a 2 by 3 matrix, and this is a 3 by 2. And so, of course, they can't be equal, even though all the same numbers appear in there. So we can use matrices to solve systems of equations. So that's where this is kind of tying back in. It's a nice way to kind of organize the details, okay? So noticing here on example 3, we have 2x, 7y equals 18, negative 21. And so if I wanted to set these equal to each other, 2x must equal 18. And 7y must equal negative 21. So solving that first entry, 2x equals 18, the only thing you do to get x by itself is divide by 2. Second entry to solve is 7y must be equal to negative 21. So we can divide both sides by 7, and y must equal negative 3. So did I need, or did you need a matrix or a set of matrices to solve this? No. I'm getting you prepared for bigger, bolder systems, okay? And so you could write then the answer as an ordered pair. X was 9 and y was negative 3. And to be quite honest, we necessarily wouldn't even call this a system of equations. If I would have said that 2x equaled 18 and 7y equaled negative 21 in the beginning of the unit, we could have just solved them separately because neither of the equations had 2 variables in it. Like x's were over here, the y's were over there. Whereas on example 4, I do have x's and y's here in the same system, or in the same equation. So looking at example 4, how would we rewrite this as a system? This would say that 2x equals y, and 2x plus 3y equals 12. This is more like the systems that we were working with earlier in the unit. So those entries correspond. This 2x plus 3y, that's all in one entry location. You can have an expression right there, okay? And so how would we solve this? Probably using substitution, right? You could subtract that y over and have it equal 0 if you wanted to use elimination. But I would take this 2x and substitute it in down here for the y. I took this 2x and plugged it in for the y. So I rewrote the bottom equation as 2x plus 3 times 2x equals 12. 3 times 2 is 6. Combining like terms, 2x plus 6x is 8. And dividing 12 by 8, we get 1.5. There's a decimal point right here. And once you know what x is, you can plug it back into the top line, and 2 times 1.5 is 3. Okay, so there is kind of the intro for matrices and how it kind of ties back into systems of equations. We're going to backtrack here just a smidge, and we're going to talk about how we could, it's called scalar multiplication. And so scalar multiplication is all entries are multiplied by the same number. All entries are multiplied by the same number. So here's an example here for number 5. It says 4 times, we want to take 4 times the matrix 6, 2, 0, negative 3. It's like the distributive property. Okay? So we're going to rewrite this as a 2 by 2 matrix, but I need to take 4 times 6, 4 times 2, 4 times 0, and 4 times negative 3. Example number 6. Go ahead and try that one. Go ahead and do example number 6. So negative 3 times 2. Let me find my red pen here.
Actually, use the
So our entries here would be negative 6, positive 18, negative 27, positive 15, negative 12, and negative 1.5. Next page. So we can add matrices and subtract them. In order to add matrices, okay, they must have the same dimensions. You must have the same dimensions if you can add them together. You have to have an entry in every single spot the same. Matrix subtraction is the same thing. Okay, matrix addition and matrix subtraction, you have to have the same number of entries. Just as 5 minus 10 is not the same as 10 minus 5, like the order of subtraction matters, the order of addition doesn't matter, like 5 plus 6 is the same as 6 plus 5. There's some things we can, and then when we get down here to multiplication, when I go to multiply two matrices together, the order of multiplication with regular numbers doesn't matter. 5 times 6 is the same as 6 times 5, but in matrices it does matter. So if you want to write that off to the side, order does not matter for addition. Order does matter for subtraction, just like with regular numbers. So it's very straightforward, guys and gals, just like that distributive property or scalar multiplication was straightforward. What we're going to do is we're going to take 5 plus 8, and that is 13. Negative 2 plus 7, 5. 3 plus 9, 12. And then you go to the second row. Negative 1 plus 1, 0. 6 plus 4 is 10. 10 plus 0 is 10.
You can put commas in.
We do not. You just space them out enough to see the separation between the rows and columns. Go ahead and try number 8, please. All right, 3 plus 1 is 4, 0 plus 6 is 6, 4 plus 4 is 8, and negative 2 plus 5 is 3. Any other questions or comments about scalar multiplication or addition or subtraction of matrices? The only thing I warn you on of like subtraction, okay? Let's say this was a subtraction sign here and there's negatives in that second parenthesis or that second matrix. Make sure that you are using, like, if you had 3 minus a negative 5, like a double negative turns into an addition problem. So those are some things that you'll need to pay attention to your integer rules there as you're going through. Okay, so those are very basic, straightforward addition, subtraction, and scalar multiplication. Let's talk about, though, matrix multiplication. Okay, get your thinking caps on here. It's almost like a puzzle of how this goes together. Okay, so be ready to go here. Matrix multiplication is to multiply two matrices together. You're going to take the corresponding rows from the first matrix and multiply it times the corresponding columns of the second matrix. And we're going to add those results together. Okay? You're going to have to add those results together as we're going. Matrix multiplication is not commutative. That's what I was just explaining. Addition, like A plus B is the same as B plus A. The order matters, okay? You cannot reverse the order in multiplication. It is not going to get you the same result. And after we do a few examples, you're going to see why. So let's go ahead and look at example number 1. First of all, what is the size of this matrix? It's 2 by 2, okay? And the size of this matrix, 2 by 3, okay? So you have to take the corresponding rows of the first matrix times the corresponding columns. We have to have the same number of rows, okay, so that of both of them, so that you can actually multiply them together. So let's take a look at this. The steps. If I have a 2 by 2 times a 2 by 3, these are the steps. We're going to take row 1 times column 1, 2, and 3. And we're going to need to take row 2 times column 1, 2, and 3. So this says R1 times C1, C2, C3, and R2 times C1, C2, C3 for rows and columns. So row 1 is 3, negative 5, and column 1 is the 5, 8. So I'm going to use these yellow boxes to kind of show you what we're going to multiply together. So we're going to take 3 times 5 and add it to negative 5 times 8. Okay? So it's row 1 times column 1. I'm going to write in green, and I think that this might be useful for you to also add that. Where did 15 come from, and where did negative 40 come from? What I write right now, you don't have to do on every example, but I think for this one example in your notes packet, it might be useful. So you need to take 3 times 5 and add it to the negative 5 times 8. 3 times 5 plus negative 5 times 8. That's 15 minus 40 or plus a negative 40. And then I work my way across, okay? So I'm going to keep using my 3 and 5, but now I need to take 3 and negative 5 times the 1 and the 4. And so I'm going to take 3 times 1, and I need to add that to negative 5 times negative 4. I'm going to see if I can line this up. And, zooming in so it's a little bit easier to see. There we go. I'm going to grab erase my highlight. Okay. Now I'm going to take first row times third column. What's that going to be? 3 times negative 3 plus negative 5 times 9. Okay? 3 times negative 3 plus negative 5 times 9. Second row, we're going to shift down, and we're now going to use the 2 and the 7. Got so much going on here. I want to move my little yellow box a little bit. Okay, there, finally. Okay, so now we're going to take 2 times, we're going to need to go back to that first column then. Right? So 2 times 5 plus 7 times 8, right here. Two times 5 plus 7 times 8. Next keeping my rows the same. Going to the second column, 2 times 1 plus 7 times negative 4. Last row times column, 2 times negative 3 plus 7 times 9. So what I'd like to see on your paper when I'm asking you to multiply would be to have what's written in pencil here. Show me what you are going to add together, okay? And then your final answer is just then 15 minus 40. Is the negative 25. 3 plus 20 is 23. Negative 9 minus 25. Negative 54. 10 plus 56, 66. 2 minus 28 is negative 26. Negative 6 plus 63 is 57. If you want to write what I had in green and have 3 sets of matrices, I think that's totally okay. Okay? I, in high school, definitely used that to my advantage, having 3 sets. I wrote it out like long ways for the first several class periods where I was learning about them. Okay? So on example number 2, I'm going to let you kind of start exploring this. First row, first column. So 5 times 6 plus 3 times 9. If I push my yellow box over, 5 times half plus 3 times 7. The results of my bottom row would be negative 1 times 6 plus 4 times 9. And then I push this across, this entry down here, negative 1 times half plus 4 times 7. So we're going to 30 and 27, 2.5 and 21, negative 6 and 36, negative half and 28. So 30 and 27 make 57, 2.5 and 21 is 23.5, negative 6 and 36 is 30, and negative half and 28 is 27 and a half. So you're going to have the opportunity to practice that a few times today on your homework. Write down anything that you need to write down, following the algorithm. Example number 3, if E is a 3 by 2, and F is a 3 by 2. It says find EF. This is an example of a problem that that is not possible. Okay, so we have to check the rows and columns. It's not possible because row 1 has 2 entries, like my rows, but the columns has 3. So I would take 3 times 4 and 2 times 6, but I wouldn't have another number here to take times the 10. Okay, so the number of rows has to be the same as the number of columns. The number, if you're going to write this part, the number of rows must equal the number of the columns. So the number of entries in the row. The number of numbers in the row. So if you want to think of it as columns and rows, it's the number of columns of the first has to equal the number of rows of the second. Columns of the first has to be the same as rows of the second. And example number 4, last example for today, I would like you to multiply G times H. I'm going to go ahead and give you 2 or 3 minutes here to get started on this. Okay? Go ahead and multiply G times H. So your solution is going to be a 2 by 3. So you need to take 2 times, multiplying these numbers, times all of these. So let's row by column. 2 times 0, 6 times 10, 4 times 3. And then 2 times 1, 6 times 2, 4 times 11. Stick with your first row here and take it times each column. Then go to second row times each column. I'll write out the first one. We have some people done with like this first like box here. So I'm gonna start showing these numbers. You can keep working if you're adding them up right now. Let me know if you disagree with any of these numbers in this first matrix here. If you'd like me to look at yours with you, I can. And this is what your sums should have been. One thing I'll point out is right here where it says minus 16. I personally probably would have wrote plus a negative 16. Right here I would have wrote plus a negative 9, plus a negative 33. Just like that's just how I see that in my head. Down here this didn't show up. It's 119 in this corner right here. All right, so that concludes section 1 and section